So, now in the previous discussion, when we have calculated the endurance strength of the material, which we always call that as uncorrected endurance strength of the material or uncorrected fatigue strength of the material, which we have designated with SE dash or SF dash. SE dash is our uncorrected endurance strength. But this please note that this endurance strength data has been obtained by doing a standard. For instance, if we are talking about pure fully reversible bending, we are actually talking about standard rotating beam bending test. However, in the reality, when in the real applications, the specimen geometry and the conditions under which the original test data has been obtained are going to be different from the real world applications, and hence one needs to account for these variations between the test conditions and the real life conditions, right. So, in order to do that, people have come up with certain correction factors based on the known differences between the experimental conditions and the real life application situations. Okay. So, in order to account for that, the SF prime or SE prime obtained from experiment should be corrected for following factors. What are those factors? A load factor, environmental factors such as temperature factor, reliability factor, size factor and surface factor. Once you have accounted for these factors, now your corrected endurance strength or SE dash is multiplied with all these factors, is obtained by multiplying all these factors with the uncorrected endurance strength. So, you can write my SE dash corrected endurance strength, this is I call corrected endurance strength is equal to C load, C surf, C size, C temp, C reliability or whatever, if there are more, times SE dash. And what is this SE dash? This is our uncorrected endurance strength. That is equal to 0.5 times SUT. We know that for steels is SE dash equal to 0.5 times SUT. Okay? And now, in order to use this information of the endurance strength for real world applications, real time applications, you need to account for these discrepancies between the conditions under which experimental data has been obtained as vis-a-vis the conditions under which the actual component works. Okay? So, let us go by each and every factor. First factor that we are going to focus on is something called load factor, called C load. If you know that the rotating beam bending test data is obtained by applying the load, the basic load is your bending load. So, if your real world application also is subjected to the bending load, then you use load factor to be 1. But the real world application is using axial load factor, then you should use a load factor of 0.7. So, these load factors, these numbers are obtained by experience. People have done several experiments and then they observed the behavior of application of these the behavior of the systems under different kinds of loading scenarios, and then they have prescribed such a load factor, and which seems to work well with the real life applications. And there is not necessarily, there is no physical basis necessarily for choosing exactly by 0.7. This 0.7 comes from the experience. Sometimes it can be 0.68, 0.72, but 0.7 seems to match with the experimental data or the test data in the real world applications pretty much, and hence when your load is different from bending load, and if it is axial load you take 0.7, if your component is subjected to pure torsion, then we calculate, what we do is we calculate the von Mises stress from pure torsion. When you have pure torsion, you know that your principal stresses are sigma 1 equal to minus sigma 3, and from there you calculate the equivalent stress and you use that stress as your bending stress, that is the load that you are going to consider being applied on the material. And if you are doing that, then you can still use C load equal to 1, because you have converted the otherwise torsional loading into equivalent normal stress which can be correlated with your bending stress situation. Okay. All right. So, we know how to choose C load. If it is bending, it is 1. If it is axial load, C load factor will be 0.7. That means, if you are applying an axial load, your endurance strength is going to be 0.7 times your bending load scenario. That means, endurance strength reduces, which is to be expected, because we have seen already when you are having an axial load scenario, the entire cross section is subjected to the same amount of maximum stress, and hence there is a higher probability for cracks to experience, more number of cracks to experience higher stress, and hence it will fail much quicker, and hence your endurance strength in the case of axial loading should be lower than the endurance strength in the case of bending. So, that is why the C load comes down. And the next factor is size factor, and the reason why we have to include this size factor is because the rotating beam bending test does use a specimen size of 8 mm diameter, right. It uses a cylindrical specimen of diameter 8 mm. However, the real life scenario uses different sizes of the components, right. The component size need not be 8 mm in all the 8 mm all the time, but if you have a larger size, you know that the larger size is expected to have more number of cracks, and hence compared to the smaller size one, and hence the failure phenomena is not going to be same as the 8 mm diameter size, and hence you need to account for this difference in size when compared to rotating beam bending test. If the part size is larger than this, a strength reduction factor should be used, because large parts fail at lower stress due to high probability of flaw being present in larger stress region. For an axial loading case, C size equal to 1, as the failure in axial loading is independent of the cross sectional area, right, because you are already taking into account of the effect of axial loading in C load, and now independent of the cross sectional area, everywhere you will have same stress. So, that is already taken into account in the C load scenario, and hence when you have an axial load, your C size will be 1, it need not be taken into consideration. Only when you have bending or other loads you need to be worried. So, for the prescription is for D less than or equal to 8 mm, C size equal to 1, because if it is less than 8, then it is not going to be worse than 8, and hence C size, you can, to be conservative, you can take C size equal to 1. For C size, for the diameter of the rod being between 8 and 250 mm, then the C size is calculated, the size factor is calculated from this empirical formula, and this empirical formula again is obtained by conducting several experiments, and this particular empirical formula seem to fit the data very well, right. There is no, again there need not be any physical basis for obtaining this empirical formula. It is obtained by looking at the experimental data, so and then fitting a curve to the experimental data. All right. If your D greater than 250 mm, then your C size is 0.6, you will play to the C size 0.6 and you will not reduce it below that. Okay. And please note that this equation or these combinations are valid only for steels. For non-ferrous metals, the equations are not actually precise. So, you need to look into the data tables, design data handbooks, and see what is the C size for a different kind of material, but for steels this is what is prescribed. In this course, we will primarily be using steels for design, and hence we are not presenting the details for other materials, but if you want the details of size factors, that should be available in the literature or design data handbooks. However, there is an important assumption here, that is your component is a circular cross section, because we are only talking about diameter. So, what happens when you have non-circular cross section? So, please refer to Norton's machine design textbook, wherein how to deal with non-circular cross section is presented in detail. Okay. So, let us look at, I will explain briefly how one should deal with non-circular cross sections and also non-rotating round bars. If it is not rotating also, it is important, because if it is not rotating, then the same material point is actually not the material point that is under high stress region probably continues to be in high stress region, and so on. So, this is also important to see what is a non-rotating, what happens for the non-rotating bar and non-circular cross sections. So, this is the prescription. One needs to obtain an equivalent diameter by equating the volume of the material stressed above 95% of its maximum stress. This is the prescription with a similarly stressed volume of a rotating beam specimen. Suppose if you take this rotating cross section of a circular rod, and we know that the maximum stress is the outermost layer and 95% of the maximum stress is at certain distance, right. Because it is linear, you can say that it is 0.95 times d, this diameter will be 0.95 times the diameter of the d. So, now we are actually looking at the area, and out of plane distance is uniform. So, I am not considering length, instead of considering volume I am calculating the area, both are equivalent in this particular scenario. What we need to obtain is the material stressed above 95% of its maximum stress. So, this is the maximum stress, here 0.95 times maximum stress. So, this region is the one that is actually subjected to stress above 95% of the maximum stress, right. And hence A95 represents area that is subjected to 95% or more of the maximum stress, that is given by pi times pi by 4 d square, pi d square by 4 minus pi times 0.95 times d square by 4, and that comes out to be 0.0766 d square, right. Now, you calculate the equivalent diameter is equal to square root of A95 by 0.0766. So, now if you have a different cross section, all that you need to do is you calculate the A95 of that cross section and plug in that value here, and then you calculate the equivalent diameter. Okay. So, let us see one quick example. For a rectangular cross section, you know that A95 is 0.05 times BH, right. That is the area that is available, that is actually subjected to greater than 95% of the maximum stress. So, all that you need to do is, in order to calculate the equivalent stress, you plug in A95 equal to 0.05 times BH, and then calculate what is the equivalent diameter, and then see what is the diameter. If it is less than or equal to 8 mm, your size factor will be 1. If it is greater than 8 mm, then you will use this formula to calculate the size factor. So, all that you do is the d is replaced by d equivalent for non-circular cross sections. Okay. So, for different cross sections, the A95 values are calculated usually in the literature, and they will be available in the design data handbooks. Otherwise, you can also, if your geometry is simple, then you can actually calculate that too. Okay. For non-rotating circular bars, your A95 is 0.010462 d square, and that is what you need to plug in here, and then you will get the d equivalent A95. All right. So, that is about size factor. So, you can now, so we have looked at the load factor and size factor, and now the surface factor. What is the surface finish of the material is going to significantly influence the fatigue strength of the material, right. The rough surfaces reduce the fatigue strength and smooth surfaces increase the fatigue strength, and hence you need to account for this surface finish. If you see this graph here, the mirror polished surface, extremely well polished surface will have a surface factor of 1. That means you do not actually have to account for reduction in the fatigue strength, whereas all other, for instance fine ground or commercially polished, machined surface, hot rolled surface, as forged surface, and sometimes you have a material that is corroded in water or corroded in salt water, all these things are going to contribute to surface factor, and this surface factor is known to be dependent on, so it is going to be different for different materials and known to be dependent on tensile ultimate strength of the material. Okay. So, you have these kind of graphs available in the literature. So, by knowing the ultimate strength of the material, you can go to this graph, and then different suppose if you know that material is machined, and if it is a 200 MPa ultimate strength, you go here and then you identify my C surf to be 0.62, right, and so on. Sometimes you can also this people, after having generated this table, these graphs, they also have given a empirical formula C surf equal to A SUT power B. By knowing SUT, you plug in, and A and B are given for different surface finish, right. A and B are given here. If your units are in MPa, use these A and B. If your units are in KPSI, use these A and B, right. If by doing such a calculation, if at all you get C surf greater than 1, then you have to use C surf to be 1 only. You should not increase your endurance strength. Only if it is less than that, then you will take C surf equal to whatever is obtained from this calculation. All right. And now the next factor is the temperature factor. Usually the rotating beam bending tests are done at room temperature, and hence correction should be made for service conditions. Up to if the component is working below 450 degrees Celsius, this is typically we are doing it for steels, but for other materials also similar expressions should be available. So, for T less than or equal to 450 degrees Celsius, your C temp need not be changed, it will be 1. If at all it is between 450 and 550, then you need to use C temp to be this guy. Usually we the regular steels are not employed beyond 550 degrees Celsius, but if at all you have some components working beyond 550 degrees Celsius, then you need to look into the design data handbooks and then appropriately identify what should be the C temp empirical formula as a function of temperature. And please note that this temperature here is in degrees Celsius, not in Kelvin, that is important, all right. And the reliability factors, because we know that the reported strength data in the literature are not definitive, which means they have a range, there is a standard deviation, there is an error bar associated with the strength data, and there is always some scatter. So, you need to take care of this, the presence of the scatter, and hence you take care of that through the reliability factor. So, if your reliability is very low, then you need to not worry about, if it is 50% reliability is what you are expecting of your component's performance, then you give your C reliability 1, and if you increase the required reliability, I want to have my component to be lasting for the component, my prediction should be as accurate as possible. That means if I increase my reliability factor comes down, which means my endurance strength of the material should be lowered accordingly, so that I can have higher confidence on the design, right. So, these are the information that is even given for reliability factors, and then please note that this is given for standard deviation of 0.08, right, because that is typically for endurance strength of steels has a standard deviation of 8% of their mean value, and based on that these reliability factors have been obtained. And this is again, as we have discussed, it is true for steels, for other materials this may be again different. So, now we have looked at all these factors, we have looked at load factor, we have looked at size factor, surface factor, temperature factor and reliability factor. So, we have looked at 5 correction factors. Once you have these 5 correction factors, after calculating these 5 correction factors, you need to correct your endurance strength by using the formula SE, the corrected endurance strength is equal to C load times C size times C temps times C surf times C reliability multiplied by C SE prime. SE dash is your uncorrected endurance strength. Okay? And when we are talking about the SN diagram, we are actually talking about the HCF regime, which is known to be active between 10 power 3 and 10 power 6 cycles, primary for steels, and for other materials is beyond 10 power 6 cycles. Then what is this SM, right? That means what is the endurance, what is the stress amplitude corresponding to this 10 power 3 cycles is denoted by SM, which is nothing but material strength at 10 power 3 cycles. If the loading is bending, then SM has to be taken as 0.9 times SUT. If the loading is axial, then SM has to be taken as 0.75 times SUT, very important to know. And should never apply correction factors to SM. Correction factors are not applied to SM, correction factors are applied only to SE dash. Okay? If the material exhibits a knee or an endurance limit, then the corrected SE is plotted at 10 power 6 cycles, not the uncorrected one. If there is no knee, corrected SF endurance, this is not endurance strength, this is fatigue strength, because there is no endurance limit, is plotted at 5 into 10 power 8 cycles. Okay? These are the guidelines. And the equation of the line that we are talking about S equal to A n power B is true from SM to SE or SF. So, log S is equal to log A plus B log times n, and A and B are obtained by plugging in the boundary conditions. Okay? That is how you would plot an estimated SN diagram. Okay? So, how do we do that? So, you have 10 power 0 cycles, 10 power 1, 10 power 2 and 10 power 3, 10 power 4, 10 power 5, 10 power 6. And now let us say this is my SUT, and let us say this is my 0.9 SUT, and let us say this is my 0.5 SUT. Okay. So, as we have discussed, the HCF regime is from 10 power 3 cycles. So, that is my first point on my SN that is the point SM, and SE is here, and that is my straight line, that is my S equal to A n power B. The first point is here. We are not, this line even if you extend here, actually it is not valid beyond this point. From here to here, because the material has to fail in LCF regime. So, that is this another line, but we are not concerned about this line at this point of time. We are doing stress life approach. Stress life approach is only applicable in the HCF regime. So, we are only talking about this line, and then it is straight line here, right. If it is not a material which does not, if it is a material which does not show endurance strength, what you need to do is let us say this is 5 into 10 power 8, then your 0.5 times SUT, the SE dash will be here, and hence your graph will be that. That is your S equal to A n power B, right. All right. So, that is how we just now have shown. Let me see if we have, yeah. Now, let us do this exercise problem, then we will see how the SN diagram can be created. So, create an estimated SN diagram for a steel bar and define its equations. How many cycles of life can be expected if the alternating stress is 100 MPa and 400 MPa? It is exactly the same problem, but now we have to incorporate the correction factors. Ultimate strength is 600 MPa, estimated strength at 10 power 3 cycle is 0.9 SUT, sigma UT or SUT. The bar is 150 mm, it is not 8 mm, 150 mm, and hence you need to account for size factor, and it is a square shape, right. So, you need to account for this 150 mm bar of square shape. So, that means the size of the bar, the square bar is 150, side is 150 mm, and it has hot rolled finish. So, this tells you, this statement tells you that you need to account for C size and C surf. The need for C size is, it is not a circular bar first, it is a square bar, and right away you have to account for size factor. And the hot rolled finish, so if it is only mirror surface, then the surface factor is 1. For all other finishes you have to have surface factor, and the operating temperature is 500 degrees Celsius. We have a guideline that if your operating temperature is less than 450, then you do not have to have temperature factor, but if it is more than 450, you need to have C temp, temperature factor. Loading is fully reversed bending. So, C load should be 1, because it is fully reversed bending, which is exactly like our rotating beam bending test, and infinite life is required. That means, we are actually talking about endurance strength, and a reliability factor of 99.9%. It is not 50%. If it is 50%, reliability factor is 1. If it is more than that, then you need to calculate what is my C reliability, right. So, let us see 99.9%, the reliability factor is 0.753. So, we can right away write C reliability is equal to 0.753, and C temp 550 degrees Celsius, C temp is equal to 1 minus this working temperature is 500 minus 450, 1 minus 0.0058 into 50, because the difference will become, because operating temperature is 500 degrees Celsius. So, 500 minus 450 is 50, and hence 1 minus 0058 into 50. So, this will be 1 minus 0.0058 into 50, that will be my C temp, and C surf hot rolled finish and SUT is equal to 600 MPa, right. So, you can see here hot rolled SUT is 600. So, 57.7. So, 57.7 into SUT should be put in MPa to the power, B is minus 0.718, whatever it comes out to be, that will be your C surf, right. C size we need to calculate. What for C size, what we need to do? We need to know that A95 for a square cross section is 0.05 BH for rectangular cross section. So, this is 0.05 times 150 times 150, because the square 150 it is same. So, that will be what? A95 equal to this value, and then D equivalent will be under root A95 by 0.0768. Is that correct? Yeah, 0.0766. And you calculate D equivalent, and from there you know what is the formula for C size, plug in that, and then you will get the values. So, the values are calculated. So, A95 is 0.07 BH, 0.05 BH, that comes out to be 1125 mm square, and then you plug that in, and then you calculate D equivalent. From the D equivalent you calculate C size using the formula that is given. Similarly, C surf comes out to be 0.584, C temp comes out to be 0.71, C reliability comes out to be 0.753. What is our SC dash, by the way? SC dash is equal to 0.5 times SUT, that equal to 300 MPa, that is our uncorrected endurance strength. But now by putting in all these factors, the endurance strength has reduced significantly, right, almost by 3 times or more than 3 times, right, almost by a factor of more than a factor of 3. So, now the corrected endurance strength comes out to be 70 MPa. Now, you see what happens. This is the figure when you have drawn this is your SM and this is SUT, and now if you take this data and A comes out to be this, B comes out to be that, and then you can actually draw this line, and we are talking about 70 MPa. What are the two conditions that we are asking? What happens my stress amplitude is equal to 100 MPa, and what happens when my stress amplitude is equal to 400 MPa. You can clearly see that at 100 MPa it fails, it gives you a life of say 3 into 10 power 5 cycles, whereas for 400 MPa somewhere here it will give you a life of about 2 into 10 power 3 cycles, right, that is corresponding to 200 MPa. Please note a major difference. Previously the same problem has been done without applying correction factors. At that time we have found, I will go back and show you, without applying correction factors we have solved this problem here. Without applying any correction factors, this is exactly the same problem, 100 MPa load, stress amplitude turned out to be perfectly fine, safe, right. However, after applying the correction factors, you have clearly seen that the material is not safe anymore even at 100 MPa stress amplitude, right, as we have seen clearly here. So, that means it clearly demonstrates to us that the correction factors are an important ingredient that needs to be considered while doing the design of components for fatigue life. Okay. With that I will stop here, and then we will resume from here in the next class. Thank you.